All right, so this is unit 6.1, starting to talk about random variables. So in this section, 6.1, we'll start to understand what a random variable is, look at some probability distributions, and do some calculations and some interpretations of situations that require probability distributions and or have random variables in it. A little bit of a hodgepodge here, so it'll seem like this is kind of going all over the place, but it'll all start to kind of connect once we continue in this unit. Okay, so first things first, kind of just describing a situation here. So remember that a probability model kind of looks like this, right? You have values and then you have the likelihood of them happening. Let's say we were looking at a probability outcome for tossing a fair coin 3 times. Okay, so the sample space, remember sample space is all the different possibilities here, is those 8 different things in that specific order. Heads, 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 tails. Those are the 8 different things that can happen if you consider tossing coin 1, then coin 2, then coin 3, and looking at heads and tails. Okay, all of those outcomes are equally likely, so the probability is 1/8 for each outcome. Okay, we're going to define a variable. Okay, this is where this idea of random variable is going to come in. X is our random variable, and it's be called the number of heads obtained. So we're going to do this process of flipping a coin 3 times, and I want to consider the variable X to be the number of heads attained in those 3 coin flips. Okay, so the value of X is gonna depend on how many heads you get, right? So the lowest value for X is going to be 0, and that's a situation when we get no heads, all the way up to 3, which is all heads, and then in between. So even though each of these 8 outcomes happen with equal opportunity or equal chance of 1 out of 8, getting 0 heads, 1 head, 2 heads, or 3 heads individually is not equal, because there are multiple ways to get 1 and multiple ways to get 2, right? Those are different orders, so those are different ways, opportunities. And so we end up with this probability model here, okay? This probability distribution. You could see it called both of those ways, probability model, probability distribution of X. Remember, X was the number of heads obtained. So what this says is that 0 heads comes up 1 out of 8 times, right? That's all tails. 1 head and 2 heads comes up each 3/8 of the time, and then 3 heads is 1/8 of the time, okay? So using that probability model, this is nothing new yet, okay? What's the probability that we can get at least 1 head in the 3 coin tosses, okay? So basically I'm saying probability of X, remember X was heads, number of heads obtained, greater than or equal to 1. So this says right here what this says right here, okay? X was defined as the number of heads obtained in this chance process. So if X is greater than or equal to 1, I want the number of heads to be 1 or greater, which is at least 1. 2 ways you could do this, okay, using this probability model, okay? 1, if it's going to be greater than or equal to 1, that means it could be 1, or could be 2, or could be 3. Now, this is not the way we've done at least 1 in the past in Unit 5, because it was a little more challenging. Here, it allows us to have the ability to do this, because we don't need to, we already counted the ways, right? We already counted the number of ways that you could get 2 or 3. So that was already kind of considered here, and we could just add those 3 different probabilities up and get 7 out of 8 different times, you're going to get at least 1, okay? The way we did it in Unit 5 is the second method here, and this basically says at least 1 is essentially the complement of not 1 or more, which is less than 1, and the only value that's less than 1 is 0. So basically what we've done in the past is if it's not at least 1, it's none. So the probability of none was 1 out of 8 times, but I don't want that, so it's 1 minus that. You still get the same answer as you did the other way, okay? So again, this is kind of just thing we already know, but then starting to apply this random variable idea, which we still haven't really considered what that is yet. No way do you know what a random variable is yet, but now we're going to start. Here's what a random variable is. A random variable is some sort of question or some sort of scenario or something that happens in which the numerical values describe the outcomes. Okay, so it's some chance process or something that happens, some survey, something happens where the outcomes are numeric values. Okay, it's not, did you eat pizza, yes or no? Okay, it's a quantitative variable type situation where your answer is going to be a number. How many heads were there? There was 0. There was 2. Okay? And then the probability distribution is what we have seen before with the model. It gives all the outcomes and their probabilities. So this box here in a nutshell just kind of says what we kind of already know, okay? We have our probability model, which gives us our various values and our various probabilities. We know that each probability has to be between 0 and 1. That's simple probability. And we know that the sum of the probabilities has to equal to 1. That's basically what we already know about probability models or distributions, okay? That's what you need to take away from there. You already know that stuff, okay? There's nothing new there. Here's something as a good reminder. We've talked about discrete and continuous random variables before, or discrete and continuous variables, maybe not random variables, but discrete variables. We'll talk about continuous a little later, but here's what discrete are. Discrete are, again, kind of a station-to-station, integer-type values. The number of siblings someone has could be 0, could be 1, could be 2. You're not going to say 4.3875. Okay, you might think of one of your siblings as a 0.3875 of a sibling, but that's not how it actually works, right? The number of free throws made in 10 tries is a whole integer value, 0, 1, 2, 3. Number of aces pulled from a deck, 0, 1, 2, 3, 4. Okay, none of these are decimal, finite. They're finite, right? Integer to integer type values. Okay, if you want, try to think of 2 more examples. That's fine. But the problem is here, just making sure you understand this. The fact that this is a random variable means that your answer is a numeric value. So the number of siblings someone has, again, not only is it integers, but it's got to be numbers, right? So that's where your 2 more examples might come from. Is the number of pencils in a box, or my daughters have, my kids have a bunch of different boxes of markers, and some of them have missing markers. So the number of markers in a given box, okay? Some boxes are bigger, some boxes are smaller, some have more missing, whatever. But the answer is going to be somewhere between 0 and who knows what, 32 or something like that, okay? All right. So this is a real thing, okay? There's something called an APGAR score, all right? When I'm making this video, my son Jackson was just born about a month and a half ago. So depending on when you're hearing this, you might know about my son Jackson. So you would know how long after this is. Okay. So in this question, or in this problem, we see Dr. Virginia, I think I spelled that wrong, Virginia APGAR. There's an APGAR score. The babies are born, and literally minutes later, you are given a score for your baby, okay, right? You're already rated the moment you're born. And this is on various things related to skin color, heart rate, muscle tone, things to kind of show whether or not the baby is relatively healthy. Obviously, there's so many other things that could happen here. But generally, like, how does the baby look right now, a minute or a couple minutes out of, the mom, okay? So my son, I mentioned Jackson, we just had this, I believe he got a 9, if I remember correctly, it was about a month and a half ago, which, as we'll start to see here, is kind of a typical score, okay? So here's what this probability model says. Basically what they did was they took 2 million newborn babies in a single year. 2 million. It's a lot. And they wrote down all of their different individual APGAR scores. Now, why is this a random variable? They didn't ask the baby their score, because the baby can't talk, but they collected data, and they said, what is your APGAR score? Because the defined random variable x is the APGAR score, of a randomly selected baby 1 minute after birth. Okay, so they said, what is your score? And the data or whatever said this baby's score was a 6. This baby's score was an 8. So 1, it's discrete because it's integer type values, and 2, it's a random variable because the answer is a numeric value. Okay, it's not a yes or no. They didn't say, did your baby score 5 or higher, and the answer was yes or no. It was, what was the score, numeric value. Okay, so what this shows you here is the APGAR scores, anywhere from a 0 to a perfect 10 in this case, and the relative probability of which they happen. So as I mentioned, Jackson, I believe all my kids were a 9 or an 8, but somewhere in there, Jackson would fall into one of the 43.7% of babies that got a 9, essentially, okay, is what that's saying, all right? So this is not probably the main thing of what we're going to do this unit, but it is a good question that kind of comes up here, is first of all, the question here says, how would we show that the probability distribution of random variable x, remember x being the APGAR score, is legitimate? We'd have to take these probabilities and add them up to 1, because again, it needs to talk about 100% of the population or the outcomes that we're talking about. We're talking about 2 million babies here. Okay. The next question is, here's a histogram representing the probability distribution. So what this would be is it's like an APGAR score of 0, 1, 2, 3, dot, 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 all the way to 10. And the height of the bar is the relative probability. So you can see that the 9 bar is the tallest because it has the highest probability. Okay, so whether you think of this as number of babies or probability, it's essentially the same thing. Whatever 43.7% of 2 million is this number. Or you could just consider it 43.7. I don't know what the label is over here, whether it's percent or number of babies, but either way, it would be the same graph, okay? Just as recalling previous knowledge, we want to describe this distribution. So let's see if you remember how to do this. If you want to take a second, try to see if you can do it. If not, I'm going to keep going here. Remember, this is Sox. Okay, not my favorite baseball team, SOX, but the SOCS in context. So the first S is shape, clearly skewed left, shape of the histogram or shape of the distribution here. O is outliers. Now this is tricky, using the 1.5 outlier rule. You need to kind of see what's happening here, okay? How would you figure out what an IQR type situation is? So what I have here is a 5-number summary. Let's talk about this real quick. Again, this is not the main most important thing about Unit 6, but it is something that can come up and something that makes sense with this and applies to previous knowledge, so it's not a bad idea to look at. Obviously, the minimum score does happen every so often is 0 and the max is 10. How would you figure out the median? Well, isn't the median the 50% mark, right? And this accumulates from 0% all the way to 100%. So if you start adding up the relative probabilities or the relative frequencies here, you start adding these up, at some point you're going to get to about 50%. You're going to probably pass 50% in somewhere. And in this location right here, somewhere within the 8s, like if you lined up all the 8 babies, at some point in time in the middle of those 8 babies, you're going to find the 50th percentile, the 50% mark, okay? It's going to be somewhere in there. So 8 is your median. Similarly, you could find the 25th percentile and the 75th percentile, probably going backwards 25% would make the most sense for that one. And then you can do a 1.5 IQR. So the IQR here would be 1, since so many of them are packed there with 8 and 9. 1 times 1.5 is 1.5. When you subtract 1.5 from 8, you get 6.5. So anything below 6.5 would be considered an outlier. Essentially, all these guys here are considered outliers. Okay, that's kind of how you would do that. It's interesting. Okay, you should be able to think through that. Okay, it's not the easiest thing to do. It might not be an AP type question, but it's a good thought-provoking type thing. So that's kind of how you would figure out whether there's outliers. Skewed data center can be defined by the median score, right? We wouldn't want to talk about the mean. You wouldn't even know what the mean is here yet, right? You're going to be able to figure that out here in a second. And then the overall range is 10, but the IQR is only 1. So that's saying, like, holy cow, the best to worst is really wide, but really most people are right in that smack dab in, I wouldn't say the middle, but the 8 to 9 range, okay? Doctors decided the APGAR scores of 7 or higher indicate a healthy baby. What's the probability that a randomly selected baby is healthy? 7 or higher, that's adding these probabilities up. They're all mutually exclusive to one another. They're all independent from one another. You just add them up, okay? 5 sisters all birthed their firstborn babies within the time frame of when this data was accumulated. Assuming these 5 babies can each be thought of as a randomly selected baby from this data, so like assume these 5 babies are in the data, and are from the data, what is the probability that at least one of them had an APGAR score of 6 or less? Okay, so there's 5 babies. We want at least one to be 6 or less. Remember, at least one is probably the easiest way to do it is not 6 or less. So not 6 or less is 7 or more. So we want all of them to be 7 or more. Well, we just figured out the probability of 7 or more, but we now want them all to be 7 or more. So that's a first one, and second one, and third one, all 7 or more. So that's a multiplication. Technically, 0.908 times 0.908 times 0.908 ... Or you can put it to the 5th power. But that's not what we want. That's saying all are 7 or more. We want literally not that, so it's 1 minus that. This is a review of Unit 5, okay? So, if you'd like, try this question here. Pause it and see, okay? It's challenging. There's some thought-provoking questions here. If not, I'm going to continue on, and we'll talk about it right now, okay? So in 2010, there were 13-19 games played in the NHL, hockey, regular season. Imagine selecting one of those games at random and then randomly selecting one of the 2 teams that played in that game. So we select a game and then separately select a team in that game. So there's 2 teams in a game, so it's kind of like a double random selection here. Define the random variable X is the number of goals scored by a randomly selected team in a randomly selected game. So basically you're saying like game on December 10th, involving the Blackhawks, and specifically not the Blackhawks, but their opponent, right? Somehow you randomly got to that place, okay? Again, random variable X, the reason it is a random variable is because the question is number of goals scored, and you could go anywhere from 0 to, it looks like in this season, the highest goal scoring amount was a 9 in any selected game by any selected team, okay? So random variable because the answer to the question is the number of goals, it's a numeric value, technically a discrete one, okay? You can't have 0.5 goals by a team. So what does this mean here? This means of all the different teams played, not just games, but teams playing in the games. Let's say 3 goals were scored by a team 22.9% of the time. So about 23% of the chance, 23% of the time, a team scored 3 goals. Exactly 3 goals, okay? Shape of the distribution here, pretty roughly symmetric. I say slightly skewed right, just because of this little bit over here, right? Just a little bit. Okay. Outliers, I'll let you kind of look through that. Again, same idea as last time, kind of going the 25% mark, the 50% mark, the 75% mark. Center in skewed data is always the median, plus in this case, you don't know how to find the mean yet. Again, kind of forewarning you, you will in a second here. And then the overall spread, the range comparing 9 goals to IQR of 2 goals, again, tells you a story of, yes, there's a wide range, but usually it's not that much, okay? Going through the probability distribution here, at least 6, simply 6 or more, you just add them up. No more than 3 is 3 or less, so you count 3 and then less than that, okay? And then at least 1, again, same idea. You want not none. So what is none? Subtract that from the total. Okay, so those are, again, review. I'm not going over that crazy new. That's not necessarily what this unit's going to ask you for, but different ways to kind of get an idea here. I want you to kind of start to understand what these probability models and distributions are saying, right? Probabilities of each event happening. This is tricky now. How many times did a team score 5 goals in the regular season? You might think, okay, I'm just going to get 5 goals. That happens 9.4% of the time. There was 13-19 games played, so I'm going to take 9.4% of 13-19. That's not correct. Here's why. Remember, in each game, there are 2 teams, and each of these is technically the probability of a selected team in a selected game. So even though there's 13-19 games, we have to multiply by 2 teams per game to say that there was technically 2,638 individual team played, right? Games played by individual teams, opportunities to pick, different times they could have scored 5 goals, right? Even though there was 13-19 games, there was 2,638 different times they could have scored 5 goals, and in each game, it could have been 5-5, okay? In hockey, it is allowed for ties. They do some sort of overtime thing, but still the game would be considered kind of 5-5, at least in some regard, right? Or at least in terms of in regulation, maybe, okay? So now you're saying, okay, 9.4% of the time, this gives you about 248, okay? So about 248 times, okay? And again, those probabilities were slightly rounded, right? So it's not 247.97 in this case. That doesn't make sense. It's probably because the .094 was really probably .0941 or something like that, okay? Last one here, and again, I hope you're sticking with this. This is good questions, good things to think about. Maybe not the most important thing in this unit, but still stuff to think about. how would you go about determining the approximate probability that the amount of goals scored in a randomly selected game was 2? I don't want you to calculate the probability, just kind of describe what you would have to do, okay? How could a game's total amount of goals scored be 2? Well, keep in mind, this is some sort of probability distribution of individual teams' goals. How could a total game have a sum of 2? Well, it could be a 1-1 tie, or 2-0, or the reverse, 0-2, right? And you might say, well, isn't 2-0 and 0-2 the same thing? Yes, but if it was like Blackhawks versus Red Wings, and Blackhawks scored 2-0 and 1, that's different than the Blackhawks scored 0 and the Red Wings scored 2, right? That's a different way to make 2 goals. So that's technically a different kind of outcome there. So really, if you're going to count all those ways, it's either 2 and 0, or 1 and 1, or 0 and 2. So that's kind of like a tree diagram type idea where you got to kind of multiply together and then add kind of thought process. So to get like 1 and 1, it needs to literally be 1 and 1. So the first team needs to have to happen 15.4% of the time, and the second team need to have to happen 15.4% of the time. And then you'd have to add up all the other opportunities there. Okay? So again, good things to think about. If you're like, holy cow, what? Pause it, see, go back, take a minute. Like, it's not that it's not important. It is. It's not the main thing of what you'll be doing. This might not be on the test for this unit, but it's good things to think about, okay? All right. Here's where we start to get in what this unit really is talking about. And it's talking about roulette. So we're talking about gambling. Just kidding, okay? If you're not sure, look up what a roulette wheel looks like. If you're like, hey, I don't even know what that is. You've probably seen one in a movie or something at some point in time. Basically, there are 38 different slots. It's a wheel. They spin it. You make a bet beforehand saying what you think what it's going to land on. And if you're right, you win. Okay? And you could be risky and pick a certain number. Like, let's say your favorite number is 13, and you're like, I'm putting all my money on 13. And if it hits 13, you win a lot of money. And if it doesn't hit 13, well, you lose. Half of the slots are numbered from 1 to 36, which half of the slots numbered 1 to 36 are red, while the other half are black. And then there's a 0 and a 0, 0. So that's how you make 38 slots. And those are green. So not quite half are red, not quite half are black, just a little bit less than half. Suppose a player places a $1 bet on red. What that means is they put $1 down. If the ball lands in red, they get their dollar back plus an additional $1. Like, they won $1. So what win $1 means is you get your money back plus you win. Okay? If it lands in a different color than what you picked, so not red, you just lose your money. Okay? So you don't have to give any extra. You just don't get your $1 back. So you lost, right? You lost $1. So really, the only two outcomes there in that case is you win $1 or you lose $1. This is a random chance, random process, and the outcome is a numeric value. This is a random variable. So the random variable X can be considered to be the net gain from a single $1 bet, meaning you either are plus $1 or you are minus $1. Okay? You win $1 if it lands on your color, which we said there are 16 reds. Just kidding, 18 reds out of 38. And there are 20 then that are not red, aka 18 black, and 2 green. So you have a 18 and 38 chance of winning your $1, and you have a 20 and 38 chance of losing. Okay, it seems like that's pretty close to even, right? Pretty close 50-50. It is actually pretty close. Okay, what we want to know, is why is Las Vegas and different places that have casinos, why are they in business? Is because in any game they have you play, you're more likely to lose than win. Otherwise, they wouldn't be in business. Okay? Yes, there are times when you play and you gamble that you can win, but anytime when you're probably gambling, you're more likely to lose than to win. Okay? So here's how. Here's how we figure out how much you are likely to win in the long run. Again, you could play 20 times in a row and win 20 times in a row, and you're damn lucky. Okay? But in the long run, which is what probability is, we expect to lose. Here's why. We expect to lose $1 20/38 of the time. Okay? We expect to win $1 18/38 of the time. If we multiply those, if we lose $1 by that probability and we win $1 by that probability, and we add those up, that's like what we expect to happen, right? this often we expect to do that, and that often we expect to do this. You add them up, and you expect to lose 5 cents every time you play this game. Okay? If this game was played millions and millions and millions of times, again, a long run average, not you went and played 5 times in a row. Like if this was played over and over and over, all the different times a roulette wheel has been spun and somebody put $1 on one of the colors, red or black, they are basically signing up to say, I expect to lose 5 cents every time I do this. Now, are they going to lose their 5 cents every time? No, they never ever will actually lose 5 cents on any given turn. But over the course of history, that's essentially the probability of what you expect. That's what you expect to happen, okay? Now, you might say 5 cents every time isn't a whole lot. Like, I could do this 20 times, and I only lost $1, theoretically. True, but that's not, again, how that works, okay? If you played 20 times and you just lost all 20 times, you just lost $20. You're balancing out the person that won 5 times in a row, okay? So why are casinos still in business? Why is Las Vegas still in business? Because if every time somebody played, they essentially lose 5 cents, even though that person didn't individually lose 5 cents, they are adding to the outcome of people losing 5 cents. That's what's happening here, okay? And that's what we're trying to calculate here. It's called a mean or expected value for a probability distribution, okay? If we have a discrete random variable with some sort of probability distribution, the mean, yes, that mean, the average, also known as expected value, okay, is what we're calculating. And very simply, to get the mean, aka expected value, all we need to do is multiply individual value times its probability, individual value times its probability, and then add them all the way across. Dot, dot, dot. That's what this says. Multiply value times its probability, and add them across, okay? That's it. That's all you have to do. That's what we did here, right? We multiplied the value times its probability and value times its probability, and we added across. That is the expected value or mean, okay? What this means is, like expected value or mean, if a randomly selected outcome is picked, so like basically saying if we do this thing one time, if a randomly selected outcome is picked, we expect the mean or expected value to occur on average. Okay, so now obviously that'll sound a lot cleaner when we do it in context of a problem. Okay, so like if we were talking about the roulette wheel, if a randomly selected $1 bet is picked, we expect to lose, what was it, 0.05 or 5 cents essentially, on average, okay? There will never be a single time that game is played that you actually lose 5 cents, because you either lose $1 or you win $1. But again, on average, okay? That's what we expect if we were to randomly pick one. Now, here's the hard part about this. You might be like, but if you pick one, it's either you win one or you lose $1, right? You can't lose 5 cents if you just picked one. No, but it's saying on average. Okay, on average, that's what we expect. We know in our mind that that won't ever happen on a single pick. But if I pick one of those games randomly, the best we can guess is, because you might say, well, are they going to win $1 or lose $1? I don't know. You're just guessing. The best way to be as accurate as possible is to say, what's the average? And that's lose 5 cents. Okay? It's more of a statement of what happens in the long run versus just a single outcome. Okay, if that makes sense. All right? So let's go back to the APGAR score. All right? The APGAR score, this is the same table as before. We have a relative probability of each score happening. Okay? Compute the mean of the random variable x and interpret this value. So one way to do this is to multiply, and add. It's not horrible. it's going to take a minute. Not preferable, but whatever, okay? You could do it. Now, in a second, I'll show you how you can use your calculator in a minute here, okay? But if you did that, you would get 8.128, okay? There is not a single baby out of these 2 million that actually had an APGAR score of 8.128. However, what we say is, if we select a random baby from this 2 million randomly, we would expect their APGAR score to be 8.128. That's the average, on average. Okay? We know that we could not have picked a baby that was 8.128. You don't round. That is what's the expected value of all of them, the average. Okay? Not just of one. So it is likely and probably most likely going to happen that your average is not actually something that actually could have happened, especially with discrete variables where it's an integer value. You're often going to get an average that is not an integer, okay? It doesn't ever happen individually, but it's what we would expect to happen, okay? If I said to you, hey, guess what Mackenzie's APGAR score was based on, let's assume she was part of this 2 million baby process. Your best guess would honestly be 8.128. You're going to be wrong, but that's kind of saying like that's what we would expect it to be, okay? Which again, best guess over the long run versus a best individual guess. If you actually said 8.128, you're going to be wrong. So you'd probably be more likely to say 8 or 9. But theoretically, if you're looking at all of them as a whole, it's 8.128, okay? Kind of tricky, but I think you'll start to get it, all right? All right. If you want to try this one, you can try this one. Again, you're just going to multiply, add them together, and then talk about what this means. So the mean, we get 2.851, means that if we randomly select a team in a randomly selected game, remember the question that this was about, this is the hockey games, okay? We would expect that team to have scored 2.815 goals in that game. Okay, basically on average, right? Will they have ever scored 2. There's no way to score 2.851. That's not like it almost crossed the line, but not quite. That's not what that means. But that's our best guess as to what it possibly would have been. Okay. All right. Skip the next one. We'll talk about that at some point. And then standard deviation. Now, okay. Here's the nuts and bolts of this, okay? Here's what you need to know from this. We already know what standard deviation means. Standard deviation is how far a value is from the average on average, okay? So we just figured out how to find averages. We're going to be able to figure out how to find standard deviations. Standard deviations will be how far our randomly picked thing, our outcome, is away from the average on average, okay? Same rule as before, okay? How far on average you are from the average. The bigger the number is, the more spread out the data is. The smaller the number is, the more likely you're picking something that's close, okay? The only thing you ever still need to know about variance is that variance equals the standard deviation squared, okay? As long as you remember that variance is standard deviation squared, you will be fine, okay? If you're given variance, you might have to take the square root to get standard deviation, okay? But again, standard deviation squared. Standard deviation is in the units of the thing, so variance is in the units squared of the thing, etc. You do not need to know these two equations, okay? You do not. And I'm not even going to cover them because you're going to be able to use your calculator, okay? So what we're going to do is with our calculator, which you could either do now or you could do later, is watch the video or just listen to me. I think it's actually pretty easy. If you remember from earlier units, we had a single list of data, and you would put your list in the calculator, and your list would be either the X or the L1 if you have the 84, but you would label the list up top, and then you'd put the numbers 0, 1, 3, 6, 8, whatever, okay? And then you would do menu, statistics, one variable calculations. You would still do that. The only difference is when they ask you for the lists, the first list will be that X list or the L1, whichever calculator you're on. But then the second part of this that we always skipped before is it says frequency of list, like frequency list or frequency of list, and it usually says 1. We do not want the frequency of our list to be 1. So we have our X list, or you have your L1 list. You want the frequency of the list to be the likelihood or probability of each of those things. So here's the deal. You're going to go make a list, and you're going to check it twice. Okay? Just kidding. It's almost Thanksgiving. Okay? You're going to make a list, you're going to check it twice. What I mean by that is you're actually going to make 2 lists. You're going to have your X list, and you're going to have your probability list. So you're going to have an X and Y list. You're going to have an L1 and an L2 list. And then when you do menu stats 1 variable calculations, you're still doing 1 variable calculations. In the part where it says the frequency of the list, you are now going to plug in whatever that second variable is, whether you called it a Y or was your L2 if you're on the 84 calculator. And then you will pop up with similar things to what we saw earlier of like X bar, which X bar, if you remember, is mean. And in this case, I believe it's sigma X. The SX, I think, is undefined. Sigma X is standard deviation. Okay, those are the two that we're going to work with here. All right, so you could take a list, plug it in, take the probability, plug it in as a second list, and do 1 variable calculations, menu stats, 1 variable calculations. The only difference is make sure your first list is selected. The second list is your frequency list, okay? So again, we'll try this in class. We'll practice it. Obviously, you should try it. You could try it here, all right? This was the APGAR scores. Remember, we did the APGAR scores earlier. We multiplied, added. You now don't have to do that, especially if I ask for standard deviation. If I ask for the mean, if I ask for the expected value, the mean, you can multiply, and add. If I ask for the standard deviation, you have to do the calculator. So look at the problem. If the problem says mean only and you want to just multiply and add, fine. If the problem says mean and standard deviation or just standard deviation, then just go right to your calculator. This list right here depends. But once I start asking for standard deviation, then it's immediately calculator. Don't even start multiplying. Okay? So when you do this, if you try it, you want to try this, would be not a bad idea. See if you can understand what I just said, or go back and watch the video on that. Okay, you get a standard deviation of 1.44. Okay, and remember that's that sigma x. Sigma is going to be standard deviation. We're going to see that a lot second semester of this class. What does standard deviation mean? Standard deviation is how far away you are on average from the average. Okay, so in this case, when we select a baby randomly, still got to say that, you're looking at a single selected baby. When we select a baby randomly, we expect their APGAR score, context, on average to be 1.44 away from the average. Okay? Remember the average was 8.128 for this data, right? We expect a baby score to be 1.44 units or points away from the average on average. Okay? So does that mean we expect it to anywhere to like 7 to 9? Well, kind of. I mean, in a way, there's some that are further from that and some that are closer. If we added 1 additional baby to this and the baby had a score of 2, a score of 2 is more than the standard deviation away. So technically the standard deviation would slightly go up, right? Because now the points are further away on average from the average. Although with 2 million, 1 little baby's not going to change it a whole lot, if at all. Okay, so anything you already know about standard deviation is still applying here. Okay, how far you are away from the mean on average if you select a random baby. Okay, so try the same thing here with the NHL example. Okay, take a second. I would suggest, again, making 2 lists. Not even just that's what you need to do. Make 2 lists. Check it twice, not to be funny, but do want to check it. Make sure you don't put any wrong numbers there. Menu, stats, 1 variable calculations. The first list is your X list. The second list, the probability list, has to be your frequency list. Okay, so make sure you change those variables, or the L1, L2, depending on which calculator you're using. All right, if you do that, you should get 1.63. So that means when you select a random team in a randomly selected game, we expect the number of goals scored for that team, on average, to be 1.63 away from the average. Okay? Again, the bigger standard deviation means that the numbers are spread out further. A smaller standard deviation means they're more compact. Okay, so if I compared this season to a different season, maybe the standard deviation would be higher because there was much more variability in the numbers. Okay, all right. Try this next one. Okay, this next one's a smaller set here. You might be inclined, if I just ask you to do mean, to multiply, and add. But since I am going to ask about standard deviation here, I would ask you to do the lists, okay, on your calculator. So try this, see if you can understand it, read through the question. I'll give you a minute, and then we'll talk about it. Okay, it's been 5 seconds. So here we go. Large auto dealership keeps track of sales made during each hour of the day. X, random variable. Okay, we always define that. We always say what the thing is that we're discussing here. Okay. Random variable is X, which is the number of cars sold during the first hour of business on a randomly selected Friday. Okay, holy cow, that's a lot to unpack. Randomly selected Friday. They've selected Friday. How many cars were sold in the first hour? Okay, so they show up on Friday. How many cars were sold this first hour? The answer is a numeric value, discrete, because it could be 0, 1, 2, or in this case 3. So by this chart, by the probability distribution here, it looks like there was 30% of the time they sold none, 40% of the time there was 1 car sold, 20% of the time they sold 2 cars, and the most that was ever sold was 3 cars, and that happened 10% of the time. Okay? So if you did mean, which again, if I simply asked mean, you could multiply and add, or you could have done your list. You get 1.1. So what does that mean? If we randomly select a Friday on one of these randomly selected Fridays, we would expect this dealership to sell 1.1 cars in the first hour of business, again, kind of on average, right? There's not going to be a single Friday when they actually did sell 1.1 cars, but that is the expected value, okay? What we expect to happen. Standard deviation, this is where you definitely would have had to do the lists, so might as well just do that right away, okay? You get 0.943. So again, if we randomly select a Friday, we would expect the number of cars sold in the first hour to be 0.943 cars from the average, on average. All right. This next question, skip this next one. Skip this next one. We'll talk about it at some point, okay? It's a good one to talk about, but I want to save your time. Save time here. So we'll talk about that in class for sure, okay? Because there's some extra good questions there too. So all these probability models and distributions were discrete random variables. Discrete. We're always going to do discrete and probably some sort of probability distribution. There are continuous random variables. Remember, that takes all the values in an interval of values, right? 6.8753, okay? The probability distribution of X is described by a density curve. When you have continuous random variable, we are back to our old friend, density curve, which our favorite of the density curves is the normal curve. Remember, they don't all have to be normal curves. You could have skewed curves, okay? But basically, if all of the values taken are so small that we have to have kind of a curve, a natural progression, instead of a distribution like we did just now, okay? The probability of an event happening is the area underneath. That's kind of what we've talked about in the past. And individual outcomes don't have a specific sign probability because they're so small, right? You wouldn't say, what's the probability of 1.6857? It's just kind of considered as part of a range. So when we do this with continuous random variables, we're looking more at a range of values more so than station to station, okay? Remember, as a little analysis here, the age in whole year amounts versus kind of your age in decimal year amounts. So if I said how old you are and you're like 17 or 18, right? That's probably what you're gonna say. That's a discrete answer, okay? If really we looked at like the minutes of the year or the seconds of the year, you would be something like 17.9856 years old, right? So again, that's more of a continuous idea. Break it down into smaller chunks. Don't worry about that part on the right there. It doesn't really help much, okay? All right, so here's what a problem looks like with continuous random variables. Our old friend, the normal distribution. The heights of young women follow closely the normal distribution with a mean of 64 inches and a standard deviation of 2.7. This is a distribution for a large set of data. Now choose one woman randomly, call her a Y. If we repeat the random choice very many times, the distribution of values of y is the same normal distribution that describes the heights of all women. Find the probability that chosen woman is between 68 and 70 inches tall. So why are we doing this now? It can be considered a random variable because when you say, what is your height? The answer is a height, right? It's a random variable, okay? All of the answers are a quantitative collection of data. But since we can look at 64 inches, 64.2 inches, 61.387 inches, it is a continuous variable. So we look at a density curve. And since the density curve follows the normal distribution, we are allowed to do calculations of probability or area under the curve using our old friends, normal, CDF, and potentially eventually inverse norm. So if I want to find the probability that it's between 68 and 70, remember here's kind of your curve here. If I'm looking for the probability, remember that's normal CDF. Inverse norm is when I know that this is like 30% of the data, right? I got a label. So I made this answer key back in the day when I wasn't quite sure that you need to label. Now I need to know, you need a label. So what is 68? 68 is the lower bound of where you're allowed to look. 70 is the upper bound of where you're allowed to look. When you're doing this on an AP test, if you don't label these clearly, you are going to get the points taken off. And then the mean and the standard deviation, okay? So this is nothing new, sigma and mu, okay? And if you do that simple calculation, you get 0.056. So what does that mean? If we picked a random woman, single random woman from this distribution, we would have a 0.056 or 5.6 probability chance that the person is 68 inches to 70 inches tall, okay? Again, inclusive kind of, right? It's including 68 and 70, but those are infinitesimally small since we have such a large set of data. Okay, this is thousands and thousands and millions of people is what we're talking about. All right, so try the next one. Try the next one. Similar kind of question. See if you remember this. Okay, I probably shouldn't have shown you the answer there. All right, so weights of 3-year-old females follow closely normal distribution. I made this when my oldest was 3. She is now 5. Again, I'm maybe dating myself when you watch this video. If it's 2030 and you're watching this video, Mackenzie will be 15, and hopefully you only are hearing stories about what 2020 was like, okay? The weights of 3-year-old females follow closely a normal distribution with mean of 30.7 pounds and a standard deviation of 3.6 pounds, okay? Made up these numbers, not gonna lie. Randomly choose one 3-year-old female and call her weight X. So again, her weight X is the random variable. What is the weight of the random 3-year-old female? Random variable, okay? Find the probability that the randomly selected 3-year-old female weighs at least 30 pounds. So the setup is slightly different in that we call it a random variable, but it's really just what we did in units, 3, okay? When we did normal distributions. Normal CDF, because we don't know the probability, we don't narrow the area under the curve, starting with a lower bound of 30 pounds and an upper bound of infinity, okay, with a mean of 30.7 pounds and a standard deviation of 3.6. So again, you should be writing all those things in. Also very helpful, this is a review, but also really helpful would be draw the normal curve. Okay, the normal curve helps demonstrate that you understand, that the reader understands that you understand, okay? Because if you look at this, if we're looking at a mean of 30.7 and we actually want to know if 30 pounds or heavier, like that's actually more than 50%. You can tell that 30 is actually left of 30.7 and you're finding the upper area. So we expect this answer to be over 50%, and that makes sense based on our picture there. So 57.7% or 0.577 is the probability. So basically if we select a 3-year-old female randomly, there's a 57.7% chance. So this is actually a review. The discrete random variable situation that we talked about up here is a little bit new, although it is relating to something we kind of already seen. Okay, this is calculator based. This is calculator based. Definitely different calculator functions though. Okay, hope this helps. Again, I know it was kind of all different places here. Main takeaways, what's a random variable, right? You ask a question, the random chance process, and the answer is some quantitative value. You could write that out as a probability distribution where each outcome has a selected probability, okay? And then you can find a mean and a standard deviation from that. Mean you can do by hand, Standard deviation, you can't. You have to use your calculator, so it makes sense just to use your calculator anyways, likely. Mean is the expected value that we would expect to get with one randomly selected outcome on average, and that's not likely to be an actual value that could exist, but it's more of a long-run average, as average usually is. And then a standard deviation is how far we are away on average from the average, just like we used to. And then in this case, we could do a little bit more of a continuous variable work, generally with a normal distribution. You probably won't see this without a normal distribution, but we're bringing that back just in time for when we're going to start using it in semester 2.